Hello dear students, welcome you all. So students, in today's lecture we are going to discuss very important result of thermodynamics, that is Joule-Thomson effect. This is also called Joule-Kelvin effect. This effect is basically first of all studied by a group of three physicists. They were James Prescott Joule, right, William Thomson, and Baron Kelvin, right. So they have first studied this effect through a series of experiments, right? And then after they discovered this effect, that is known as Joule-Thomson effect or Joule-Kelvin effect, right? They perform all these experiments around 1850 and they gave this result in 1852. Clear? Joule-Thomson effect, right? Why this result, Joule-Thomson effect, is important in thermodynamics? You might have seen the working of a refrigerator or a AC. So the question arises in the mind that how these machines produce cooling. So all these machines are basically based on the working of Joule-Thomson effect, right? If I give the definition of this effect, then when a liquid or a gas, we can say when a fluid is allowed to expand from a region of extremely high pressure to a region of extremely low pressure, then there is always a change in the temperature of that fluid, right? This effect is called Joule-Thomson effect, right? Yeah, Joule-Kelvin effect. So this principle is utilized in both refrigerators as well as in AC that are working everywhere around you, right? So they are basically what they are doing. They are taking a fluid, either a liquid or gas, then they are compressing that with the help of a compressor, and then they are getting it expanded adiabatically. And when the fluid is expanded adiabatically, there is a cooling produced in that fluid. So that fluid is then used for cooling the air, right? So today we will understand this effect thoroughly, and then we will arrive at the results that when the heating is produced, when the cooling is produced, how the ideal gases behave in case of Joule-Thomson effect, how the real gases behave in case of Joule-Thomson effect. So all these things will be discussed thoroughly in this lecture, right? So first of all, we will understand the experimental setup used by Joule, Thomson and Kelvin for giving this result, right? So for it, I am taking this experimental setup. There are various experimental setups which can be used, but I have preferred this one because this setup is very easy to understand and it is also given in your textbooks, right? So you can see here different parts of this experiment. So first of all, look at this. This is a constant. This is a constant temperature bath, right? This is a kind of a container that contain a liquid. Obviously, it is a water that is called constant temperature bath, right? We have placed a thermometer here to measure the temperature of this liquid, right? This is a compressor which is compressing a fluid. Suppose we have taken a gas, right, here inside this compressor, and we are compressing it with the help of this piston. When this gas is compressed, it passed through here toward this region. Now here we have one bend. You can see more than one vents here, or even spiral path here. This vent or this spiral path is made to give more time for the gas to go from here to here, so that this gas attain the temperature of this uh, medium, that is obviously butter. So when the gas finally arrive here, it has pressure P1, volume V1, and temperature T1, that is measured by this thermometer, right? Now, that's why this is called constant temperature bath. Now, the temperature of this gas is T1, pressure is P1, and volume is V1, and it is basically a compressed gas, right? Coming here. Now, this part of this experiment is a porous plug, right? Porous plug. It has very fine holes through which the gas can escape from here to here. Now this is open region, and here the pressure is P2, volume is B2 for the gas. We have taken the pressure P2, but this region is obviously as the open, so the here pressure will be the atmospheric pressure, right? And the volume of the gas will be V2, right? Now you can see here the gas was under extreme pressure, and when it is pass through this porous plug, it is throttled. It is suddenly going from a region of extremely high pressure to the region of extremely low pressure, right? So this process is called throttling process, right? Here, the temperature of this outgoing gas is measured through this temperature, the thermometer T2, right? Here we have used the insulating material. What is the significance of using this insulating material? It is very significant. Why? Because when the gas is allowed to expand from here to here, the gas will increase its volume, right? The pressure will decrease, the gas will increase its volume, means the gas molecule will try to go apart from each other. They will try to go away from each other. So they require energy for it, right? So we are not providing any energy. We have insulated this part of the experimental setup, or this section of the setup, so that no amount of energy can be taken from outside for the outgoing gas. So but that gas will do, it will utilize its own energy, and when it will utilize its own energy, then obviously the temperature of that gas will fall, right? Because the gas molecules are going away from each other, they are expanding, their volume is increasing, pressure is decreasing. So in that situation, the temperature T2 will be obviously decreased. But this is not the end of this experiment. You will see in case of ideal gases, there is no change in the temperature. This is very strange. What the temperature change take place only in case of real gases. But this is obvious, because in reality, no gas is an ideal gas. All the gases present in the nature are real gases. So we observe a change in temperature, right? So we will get all these results when we will do the thermodynamic treatment of this entire experiment, right? And we will arrive at some results, right? When we use this experiment, there are certain things that take place. There is always a change in temperature when there is adiabatic throttling of a gas, right? This change in temperature is called Joule-Thomson effect that I told you in the beginning. Uh, the change in the temperature depend upon the pressure difference, P2 minus P1 or P1 minus P2. How much is the pressure difference? That is proportional to this. Change in temperature is proportional to this. Uh, at ordinary temperature means 27 degrees Celsius. That is the normal temperature that we consider room temperature. At ordinary temperature, most of the gases show cooling effect. Clear? Means we will get cooling when the gas is allowed to expand from a region of this high pressure to the region of this low pressure. But there are two gases, hydrogen and helium. They don't show cooling, but they show heating effect, right? Why these gases are showing heating effect? So this will get cleared when we will drive the mathematical equations for it, right? For every gas, there is a certain temperature that is known as temperature of inversion, Ti. Clear? Now every gas, clear, when it is coming for this treatment, it should have temperature less than this temperature, Ti. If the temperature of that gas is less than Ti, the gas will obviously show cooling effect. But if the temperature of the gas is greater than this temperature of inversion, then the gas will show heating effect, right? And the temperature of gas is equal to Ti, means if the temperature is equal to temperature of inversion, then the gases will show neither heating or a cooling effect. Now the fact is, for most of the gases, their temperature of inversion is high, right? So the normal working temperature is always less than this temperature of inversion, so we get cooling in that cases. But for hydrogen and helium, this temperature is low, so before using these gases for this treatment, we must reduce their temperature, we must decrease their temperature, so that we get a cooling here, right? So this was the entire theoretical, discussion about this experiment, this effect. Now we will do the mathematical thermodynamic treatment of Joule-Thomson effect, right? So I told you that this effect was first of all studied by James Prescott Joule, William Thomson, and Baron Kelvin around 1850, and after performing series of experiments, they arrive at this result, that is known as Joule-Thomson effect or Joule-Kelvin effect, right? This was the simple experimental setup that was used for understanding this. And now we are going for the thermodynamic treatment of this, mathematical treatment of this effect, right? So to understand the thermodynamics of Joule-Thomson effect, we have to consider this diagram, right? Now, you can say this diagram. This is this diagram is the simplified version of the experimental setup that we have discussed, right? Here, this is the piston that is going toward this side. We are applying pressure on the gas contained here. This gas has pressure P1, volume B1, and temperature T1. Whereas this is the pores plug. Right, and this is the region where the gas is going to expand. It has pressure P2, volume B2, and temperature T2 in this region. Both these pistons are frictionless, they are free to move, there is no friction here and here, so there is no loss of energy, right? Now suppose we have applied pressure from this side, this piston moved toward this side, and now it reaches a new position, that is this one. Clear? Or I can take in this way. Right, now this piston reaches here, and when this piston will reach here, it will suppose travel a distance. This distance is x1, right? This distance is x1, right? Similarly, this piston, when the gas will pass through this pores plug, it will go there and it will exert a pressure on the piston P2, so it will move toward this side. Suppose the new position of this piston is this one, right? Now let this distance is x2, x2. Let in both the cases the area of cross section of this piston is a, right? So x1 is the distance traveled by piston, this piston A, we call it as piston A, and this is piston B. Clear? Sorry. Then work done by this piston on this gas. Clear? Obviously, W is equal to PV, so it is P1 B1. Clear? Similarly, the work done by this gas in this region on this piston, it is suppose W1 and it is W2. It is equal to P2 B2. Clear? So this is the work done by this piston on this gas here, and this is the work done. W2 is the work done by the gas that is arriving here on this piston B, W2. The difference in work W2 minus W1, that is delta W, that is equal to P2 B2 minus P1 B1. This work is done on the porous plug here. Clear? If we consider that there is no loss of energy or no loss of work due to the friction or other forces present in this region, right? Now, uh, let U1 is the internal energy when the gas was in this region, and U2 is the internal energy when the gas is in this region. Here one thing is very important, that this entire process is taking place adiabatically. We have seen in experimental setup that we have thermally insulated that uh, entire apparatus here, particularly here. So there is no energy gain from the outside. So when the process is taking place adiabatically, it means this energy is not supplied from the outside. So it means, so the change in the internal energy, that will be responsible for the change in temperature of the gas. Clear? Because when the gas will expand, as I told you, in this region, it will utilize its internal energy. So the internal energy of the gas will decrease. So I can say delta U is equal to U2 minus U1. Clear? This is equation number 1. Clear? Now we know, according to the first law of thermodynamics, dq is equal to du plus dw. Clear? But we know in this case, particular case, as the process is adiabatic, so du is equal to 0. So du is equal to minus dw. Clear? Or we can say du is equal to minus p dv. Clear? This is the result that we got when we applied the condition here, right? So I can say u2 minus u1 is equal to, now what was u2 and u1? p2 b2 minus p1 b1, but it will become plus, it will become minus, because they are linked. du is equal to negative of dw. So dw is here, I have written here, this is w, we can say dw, so they are negative of it. So u2 minus u1 becomes minus p2 v2 minus minus plus p1 v1. So if I rearrange it, then it will become u1 plus p1 b1 is equal to u2 plus p2 b2. Clear? So this is, we know u plus pb, right? It is equal to h, enthalpy, right? It is enthalpy. So it means h1 is equal to h2. That is very important. It means during this entire process, enthalpy is a constant. Clear? Clear? Now we have this equation, u plus pv is equal to h. Clear? So differentiating this equation, u plus pv is equal to h. Clear? So if I differentiate it, du plus pdv plus bdp is equal to dh. But as h is constant, so dh is equal to 0. So I got du plus pdv plus bdp is equal to 0. Clear? Now this is equation number, earlier we have written equation number 1, it is equation number 2. Clear? Now from the first law of thermodynamics and second law of thermodynamics, that is dq is equal to du plus p dv, and if I put it here tds according to second law of thermodynamics, then this equation becomes tds is equal to du plus p db. Clear? Right? P db. Right? This is equation number 3. Clear? Du plus pdb. Clear? So now I'm going to put this equation 3 in equation number 2. Right? So this equation will become, equation number 2 will become tds plus bdp is equal to 0. Clear? Let this is equation number 4. Clear? Now let's consider that entropy S is a function of pressure and temperature. Clear? S is a function of S is equal to S P comma T, pressure and temperature. Then from the theory of derivative, ds is equal to curly S upon curly T P dt plus curly S upon curly P constant temperature dp. Right? So putting this ds here, right? So what you will get when you will put it here, T bracket curly S upon curly T P dt plus curly S upon curly P T dp plus B dp is equal to 0. What I did, I put the value of ds in equation number 4, right? So now I can expand this bracket, multiply t inside it, so it will become t curly S upon curly T P dt, right, plus T curly S upon curly P T, right, dp plus B dp is equal to 0, right? I multiplied t inside the bracket, so I got this equation now. But we know T curly S upon curly T P is equal to Cp. From the thermodynamics, this is Cp is specific heat at constant pressure, so I'm going to put it here. So I will get Cp dt plus T curly S upon curly P T dp plus B dp is equal to 0. This is equation number, it was 4, it is equation number 5. Clear? Now we are going to utilize Maxwell fourth relation, right? Maxwell's fourth relation. That is curly S upon curly P T, that is equal to minus curly V upon curly T, it is P. It is P here, right? So this is Maxwell fourth relation. So I am going to use this relation here. Right? So what I will get? I will get when I put it here, Cp dt minus T curly V upon curly T pressure constant dP is plus V dP is equal to 0. Clear? Now this is equation number 6. So I can rearrange this equation. So when I will rearrange this equation and then I will get uh, and simplify it in two steps, dt upon dp is equal to bracket. I will take this toward this side, t curly v upon curly t p, right, minus b divided by c p. Clear? This is equation. What I did, I simply took these terms. First of all, these terms, I took these two terms toward this side, and then I divided this entire term by Cp, and I took dP common and take this toward this side, right? So now I got this equation. I can write it in even more simplified form, that is T upon Cp. This equation is equal to T upon Cp into T upon B, sorry, not T upon Cp, it was B upon, I took B as common. So I took this B as common, so it will not be T here. T, I have taken T outside, it would become T upon Cp. So I can write here actually B upon Cp, right? Then it will become B upon Cp, and here it will become T upon B in that case. Now it becomes correct, into curly V upon curly T P minus 1. Clear? Into not into, right. This is what I got. If I multiply this equation, or once again took dp toward this side, then it will become b upon cp into bracket t upon b, right, into curly v upon curly t constant pressure minus 1, into dp. So here we know very well that 1 upon v into curly v upon curly t is this. This is called alpha, volume coefficient of expansion. Clear? Volume coefficient of expansion, right? So if I put it here, then this equation will become dt is equal to b upon cp into t alpha minus 1 dp. Now this is the required result. Clear? This is the required result that we were looking at. Now I can once again took dp toward this side, and I can write it in this form also, that this is equal to dp. So here it will become like this, right? Right. So what this equation is telling us? This equation is telling us uh, change in temperature with change with respect to change in pressure, right? So this will tell us whether the temperature will change or not when the gas is allowed to expand from this side to this side. Clear? So this is the final result that we were looking at. Sometimes this factor is denoted as mu. Clear? Mu, right? So this is called a Joule-Thomson coefficient, right? It tells us about the change in temperature per unit, change in pressure, right? In terms of all these factors, right? So now we will discuss this result for both the cases, for the case of ideal gas and for the case of real gas, right? So this is the final result. You can give them these two results names. Equation number, it was uh, equation number 8. Clear? So now we are going to use equation number 8 for the case of first of all ideal gas. Or ideal gases. Clear? And then we will discuss it for the real gases. So we know very well what are ideal gases. Ideal gases are all those gases which obey all gas laws at all temperature and pressure. And we know gas equation for them is PB is equal to RT. If we take N is equal to 1 mole, then from here we got B is equal to RT upon P. Now differentiating it with respect to T, keeping pressure constant. Curly V upon curly T at constant pressure, then we get R upon P. Clear? And this is equation number 9. Now I am going to put this equation number 9 here in equation number 7. Clear? So curly B upon curly T, P, that I have right here, that is R upon P. So it will become RT upon P minus B here. So, right? So now you can write here dt upon dt is equal to RT upon P minus B upon C P. Clear? Now RT is PV, right? So it is what? It is PB. So P cancel, B minus V 0. So this is equal to 0, right? It means dt is equal to 0. Clear? It means T is equal to constant. Clear? So it is very, very important result that the ideal gases, clear, they don't show Joule-Thomson effect. Clear? In those cases, there is no change in temperature. Clear? No change in temperature, so no cooling or heating will take place. But this is the situation of ideal gases case I have discussed in the beginning also. In reality, we don't have any gas that is fully ideal, right? So now we will discuss the case for real gases, right? So for real gases, right? Now we will see how the real gases behave when they are given this type of treatment, Joule-Thomson treatment, right? We know very well for real gases, the equation that describe their behavior is van der Waals gas equation for real gases. Now we are taking the case of for real gases. Clear? So for real gases, we have van der Waals equation. Right? That is P plus A upon B square into V minus V is equal to RT. Clear? Now differentiating it with respect to T, clear? Keeping pressure constant. Clear? Now these are two terms, so we will have to use product rule of differentiation. So it will become P plus A upon B square, differentiation of second, that is curly B upon curly T, pressure constant, because the differentiation of this V is constant, it is a constant. That is the first case. Then plus now B minus V as constant, and the second term this as variable. So when you will take the differentiation of it, it will become minus 2A upon V cube into curly V upon curly T, pressure. On the right hand side we will left with R. Clear? So this is the differentiation according to the product rule. We have two terms, this is term 1, this is term 2, and we are doing the product rule. So after simplification, when you will rearrange it, you will get curly B upon curly T, pressure is equal to R upon P plus A upon B square minus 2A upon B cube into B minus B. Clear? Now this is equation number 1, 2 in this case. This was equation number 1. Clear? Now from equation number 1, we know very well that P plus A upon B square is equal to RT upon B minus B. Right? If I took this toward this side, then it will give me P plus A upon B square, that is equal to RT upon B minus B. I am going to put it here. That is RT upon B minus B. So when I will take it here and I will take the LCM, the things will get modified as here. It will become curly V upon curly T, constant pressure is equal to R into B minus B, denominator RT, clear, minus 2A upon B cube into B minus B square. So I took this LCM, I multiplied it here and then took it into the denominator. So now it becomes equation number 3. Clear? Since V, this is very less than V, it is understood. So we can ignore it here. So it will become B square, right? It will become B square. So it will get cancelled. We will get left with only B here. Right. When we apply this condition, we are left with V only. Then I will simplify it further. It will give me curly V upon curly T, T is equal to R into V minus V divided by RT minus 2A upon B. That will further become, when I divide the numerator and denominator by RT, here by RT, then R to R get cancelled. I will get B minus B upon T in the denominator. Denominator I will get 1 minus 2A upon B R T. Clear? Now I will take it denominator. It will become B minus B upon T into bracket 1 minus 2a upon BRT power minus 1. Now I'm going to expand it by binomial theorem and neglecting the higher order terms. Clear? Then we get this is equal to b minus b upon t, right, into 1 plus 2a upon VRT. It will become plus because of this minus term. I have ignored the higher order terms. We will multiply it, and after multiplication we will get b minus b, clear, upon I took this t toward this side, clear. So it becomes t curly b upon curly t at constant pressure. So I took it there. So it becomes b minus b, clear, plus 2a upon RT minus 2ab upon BRT. What I did, t is taken toward this side. I multiplied by this entire term by b minus b. So first term b minus b, then I multiplied b with this term. I got 2a upon RT. B got cancelled with b in the next term. 2a b minus and this. Now, right? Now again, we can ignore this term. It is very small. So we will get t curly b upon curly t p is equal to b minus b plus 2a upon r t. Clear? So this is this is equation number it was 3. It is equation number 4. Now I am going to put this equation number 4 in equation number 7 that we did earlier. Then I will get dt upon dp is equal to, I am going to put this t curly v upon curly tp. It was equation number 7. We can see here, right? T curly v upon curly p. So I am going to put it here. So I will get this is equal to b minus b plus 2a upon rt minus b upon c. B got b cancelled, so I got this is equal to 2a upon rt minus b in the denominator I got a cp. This is equal to dt upon dp, that was mu. Clear? So it means one thing is clear that dt is equal to when I took this toward this side, it becomes dp. I have erased it from here. It means dt is not equal to 0 now in this case. It means there is a change in temperature, right? So the behavior of the real gases is different from the behavior of ideal gases. In case of ideal gas, we got dt is equal to 0. That means t is constant. But here dt is not 0. It means there is always change in temperature. Clear? That depend upon these factors. Clear? So now we will discuss this result. Now dt is equal to, you can see here, dt is equal to this factor. Clear? Now as we will look at it, whether dt is positive or negative. Now you look at dp. What is dp? That is p2 minus p1. Now p1 is higher than p1. P1 is higher than P2. Uh, Obviously, initially pressure was very high, so it means dP is negative. Clear? One thing is sure. Now, dt is negative if this term is a positive. 2a upon RT minus B is a positive. If this is positive, then this dt will be negative. Clear? So in that case, we will get the cooling effect. Clear? Cooling will be produced. So this is positive means 2a upon RT must be greater than B, or we can say T must be less than 2a upon RB. Clear? T must be less than R upon B. Right? So if the temperature is less than this temperature, then the gas will show cooling effect. dt is negative. Now the second situation, suppose in second situation, this is very interesting. Suppose 2a upon RT minus B is equal to 0. If I put it 0 here, then this dt will become 0. It means again there is no change in temperature and the real gas becomes ideal gas. Clear? So it means 2a upon RT is equal to B. It means T is equal to 2a upon RB. This is very, very important. If the temperature is equal to this temperature, then the gas show neither heating, neither cooling, right? And it is behaving just like an ideal gas. So this temperature is called temperature of inversion that I talk about in the beginning. At the temperature of inversion, the gas neither show heating, neither show cooling. Now the third case, if this term, is negative, it means if it is negative, it is already negative, 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 positive. It means dt is positive. It means heating is produced in this case. If the heating is produced, then look at it. It means this equation is negative. It means 2a upon RT is less than B. Clear? In that situation, it will be negative. It means T is greater than 2a upon RB. Clear? So T greater than 2a upon RB means T is greater than temperature of inversion. Clear? So this is very important. If the temperature of the gas is greater than temperature of inversion, it will show heating effect. Clear? If the temperature of the gas is less than temperature of inversion, that was the first case. Clear? Yeah, this one. Clear? Then the gas show cooling effect. And if the temperature of the gas is equal to temperature of inversion, then there is no heating, no cooling. Right? So this is the entire result of this experiment. Now, as I told you in the beginning, that for most of the gases, we get a cooling effect. For example, nitrogen, oxygen, right? Because the temperature of inversion is a high. It is quite above than the room temperature. So when we uh, take these gases for this experiment, we get the cooling effect. But in case of hydrogen and helium, that I talked in the beginning, in case of hydrogen and helium, the temperature of inversion is very, very low. Clear? It is very, very low. So it means we will get a heating effect in case of these gases when we use these gases for this experiment, right? But we can get cooling from these gases if we pre-cool these gases before bringing them for this treatment, right? We use certain apparatus for cooling these gases before coming here, and then we will compress them and we will get the result. So in that situation, these gases will also show cooling effect. But this is very important. Under ordinary conditions, these gases, two gases, will show heating effect. because their temperature of inversion is very small. Clear? It is quite less than the ordinary temperature or room temperature. But for other gases like oxygen, nitrogen, temperature of inversion is quite higher. So in that cases, we get the cooling effect, right? So well, this was the entire discussion of this Joule-Thomson effect. I'm hopeful that the things has been got clear, very clear. Now, as I told you that this effect is used in refrigerators and in AC machines, right? So there what we are using? We are using a suitable gas, right? Then that gas is compressed with the help of a compressor, right? If I take the case of a refrigerator, right? Suppose this is the right. This is the now refrigerator. You might have seen a compressor on the back side of the refrigerator, right? So we have a compressor on the back side, right? And we are using some gas that is stored inside the this compressor unit. Now we are compressing, this compressor is compressing that gas up to a very high pressure. Then that gas is allowed to expand through the throttles. You might have seen on the back side of the refrigerator, there is a mesh of fine wires or fine tubes, right? So when that gas is allowed to pass through all this mechanism, all this setup, then the gas is throttled, its temperature reduced, and then finally it is circulated inside the this refrigerator. Clear? Through different pipes. So when this cooled gas is circulated inside the refrigerator, we will get cooling inside the gas. And then after, when the gas is circulated, obviously its temperature will increase. It will absorb the heat from the material that is kept here. So then again that gas is taken back to the compressor and it is again compressed. So again and again this cycle is repeated. So the heat from the inside is taken outside. Clear? We can say this is a heat engine working in the reversible direction. The same principle, same phenomena is used in case of ACs. Clear? So this is all about it. I'm hopeful that the things has got very clear. So thank you very much.